NASA has filmed the moment that a huge solar flare erupted from the surface of the sun.
A solar flare shouldn't look like that. Not this bright, not this fast, not this violent.
The phenomenon is a powerful burst of radiation. The Earth's atmosphere protects life on our planet, but the flares can sometimes have an effect on satellites in orbit.
The moment it erupted from the sun's surface, every observatory on Earth went quiet for half a second. Because everyone watching the feed had the exact same thought.
Our very own living, breathing ball of gas. The bright bursts of light are huge solar flare eruptions that herald a period of rare and furious action.
That wasn't a flare, that was a plasma bomb. It launched with the force of 1 billion nuclear detonations, carving a burning arc across the sun's corona, twisting into a shape no model predicted. A rose made of fire, a fist, a serpent. Scientists argued about what it resembled, but they all agreed on one thing. It was headed straight for Earth, and nothing in the last decade of solar activity compared to it.
Vast clouds of magnetized solar plasma and radiation leaping into space.
The first warning came from a probe parked near the L1 Lagrange point. It's programmed to send alerts automatically. Little coded bursts telling Earth when a solar eruption is incoming.
These contribute to what is known as the solar wind. It's a continuous flow of charged particles being thrown in our direction at around 1 million miles per hour.
But this time, the probe didn't send a warning. It screamed. A continuous, rapid-fire signal flooded mission control. That meant the CME, the Coronal Mass Ejection, was expanding faster than the instrument could log. Plasma wasn't drifting outward. It was exploding outward, accelerating, like something was pushing it from behind. And then, the numbers broke. Every dashboard, every telemetry panel, every intensity graph hit maximum. A red line across the screen that did not dip. The wave of charged particles was moving at a speed that didn't match theory. Scientists knew they had under 14 hours before impact. Maybe less. The sun had effectively hurled a burning world in our direction. The first people to react weren't the physicists. It was the military. Solar storms can blind satellites, scramble targeting systems, jam communications, and kill power grids. Within minutes, secure networks lit up across the US, Europe, China, and Russia. Space agencies coordinated with defense departments. The panic was quiet, but it was real. Then the public found out, not through an official alert, through an amateur astronomer in Arizona who posted the eruption clip from the Solar Dynamics Observatory and wrote, "Is this bad or really bad?" The video went viral in 3 minutes. By the time NASA released a calm, carefully worded statement, the internet had already decided Earth was about to be microwaved. The truth was somewhere in between. A plasma bomb doesn't act like normal solar weather. It carries intense magnetic fields locked inside superheated material. Millions of tons of ionized gas ripping across space at 1 million miles an hour. When it hits Earth, those magnetic fields can couple with our own, twisting the magnetosphere, forcing currents into the crust, overloading transformers. In 1859, something similar happened, the Carrington Event. Back then, telegraph wires caught fire. Today, the world is made of wires. We never tested what happens when everything, GPS, satellites, internet backbone, power stations, aviation, gets hit at once. As the plasma wave raced toward us, scientists tried to map its magnetic orientation. That's the key. If the field tilts upward, Earth shrugs it off. If it tilts downward, it punches straight into the planet's system like a battering ram. But the data coming in didn't make sense. The magnetic field was flipping, rotating, spinning like a coin wobbling on a table. Nobody had seen that before. Some thought the flare interacted with a coronal hole. Others thought the sun's active region twisted in the moment of eruption. a few whispered something far stranger. Maybe we were seeing a new kind of solar event, something the sun hadn't done in recorded history. 6 hours before impact, pilots were told to avoid polar routes. Airlines quietly shifted flights. Space agencies put satellites into safe mode. Power companies prepped for grid instability. Emergency rooms stocked backup generators. Governments rehearsed blackout scenarios that were never meant to be public. Still, the wave kept coming. Auroras lit up at noon in parts of Scandinavia, before the CME even arrived. That's how disturbed Earth's magnetic field had already become. Birds changed migration paths. Whales beached themselves in groups. Compass apps on phones spun like slot machines. Something was pressing against Earth's magnetic shield, remapping it before the main blast even touched us. 4 hours before impact, every major telescope turned toward the sun. The flare's origin region was still boiling, a wound of light across the solar surface. And then something even stranger happened. A second flare bloomed from the same spot, smaller but synchronized. The sun rarely fires twice from the exact same magnetic knot in such a short time. That meant the region was unstable, beyond anything sunspot models predicted. The plasma bomb was just the first punch. None of the scientists wanted to say it out loud. But they all knew what a series of flares could mean. An entire solar cycle behaving badly. Kicking off years of hyperactive weather in space. The countdown hit 1 hour. The wavefront slammed into a monitoring satellite first. Its final transmission was a static burst, followed by a hard shutoff. Not drifting offline, instant death, like a fuse blowing. That told scientists everything they needed to know about intensity. The plasma wasn't just charged, it was overloaded, carrying a magnetic spike capable of shredding circuitry outright. Then Earth's magnetosphere groaned. Yes, groaned. Space weather instruments recorded a sudden compression on the sun-facing side of our planetary bubble. Normally, the magnetosphere extends tens of thousands of kilometers outward. In that moment, it compressed to nearly half its size. If you could see it with the naked eye, it would look like someone punched Earth's protective shell inward. The shock hit 22 minutes later. Lights flickered across northern Canada. Transformers hummed with a low vibration engineers described as a lion growling. Radio frequencies dropped. Air traffic controllers lost HF communication and switched to backup protocols. Astronauts aboard the ISS retreated into shielded modules as their radiation meters spiked off scale. And then the main plasma wave arrived. It struck Earth's magnetic field like a drum hit by a hammer. The auroras didn't bloom, they detonated. Curtains of green, red, and violet light raced across the sky, visible from Mexico, India, Italy, and Japan. For the first time in history, people in tropical countries saw auroras with their own eyes. Solar particles streamed down into the atmosphere. Electrical currents surged through the ground. One power substation in Quebec overloaded so violently that the protective systems shut it down before it exploded. In the American Midwest, GPS signals vanished. Farm equipment, semi-autonomous and reliant on satellite guidance, froze in fields. In Russia, early reporting claimed several communication satellites went dark at once. But something unexpected happened. Earth held. The magnetosphere twisted, bent, absorbed the impact. For all the chaos, all the fear, the plasma bomb didn't break the planet's defenses. It injured them deeply, but didn't tear them apart. Still, the event wasn't over. The magnetic storm kept rotating. Instruments detected a corkscrew pattern like the plasma carried its own pulse, a rhythmic fluctuation scientists compared to a heartbeat. That heartbeat transferred into Earth's field, causing repeating waves of instability every 40 minutes. Each pulse triggered new auroras, new currents, new interference. People recorded videos of strange lights of blue and white rippling behind clouds, electrons colliding with nitrogen at intensities rarely seen. A pilot flying over the Atlantic reported a wall of shimmering light stretching horizon to horizon. In Australia, stargazers watched the sky flicker like a strobe as magnetic substorms cascaded across the poles. And then came the radio blackout. For 19 minutes, large chunks of the planet lost shortwave radio entirely. Ships at sea reported being effectively blind. Amateur radio operators heard nothing but a deep, rolling hiss, like the sound of the universe breathing through static. This wasn't caused by technology failing, it was the ionosphere itself being rewritten in real time. The worst-case scenario, a global power grid collapse, never fully materialized, but several regions experienced brownouts. Transformers ran hot. Engineers manually disconnected vulnerable lines to prevent long-term damage. Satellites that survived the initial blast drifted slightly off orbit due to atmospheric swelling. The storm heated the upper atmosphere enough to increase drag. As dawn approached, the intensity slowly dropped. The plasma wave thinned. The magnetic rotation slowed. The pulses weakened. Earth's field began to recover its shape, like a bruised muscle unclenching after a blow. But one mystery remained. When scientists replayed footage from solar observatories, they noticed something chilling. The plasma bomb's shape, its initial twist, its spiraling magnetic signature, didn't match any recorded solar flare in history. It wasn't random. It looked patterned, almost intentional, like the sun's magnetic field got tangled in a knot and snapped all at once.